So in this section of the notes, we're going to be looking at the reactions of the benzene ring. And as we've explained in previous videos, the benzene ring is a lot less reactive than it's expected to be. So you need some really quite strong reagents to get the benzene ring to react. The other thing you should notice about the benzene ring is it doesn't undergo the typical addition reactions you would expect of a species with double bonds in it. Rather, it undergoes substitution reactions because this maintains the ring stabilisation. So in excess air or oxygen, benzene, like any other hydrocarbon, burns to form carbon dioxide and water. So we have our molecule C6H6. We're burning it in 7.5 moles of oxygen to form 6 carbon dioxides and 3 water molecules. It burns with a very smoky flame, and that's because you've got a very high carbon to hydrogen ratio, and sometimes we can use that as a test to indicate the presence of a benzene ring. So an electrophile is a species that are attracted to areas of electron density. To do this, it needs a vacant orbital. So an electrophile is a species with a vacant orbital, where something can put a pair of electrons. So good examples of this would be things like the NO2 positive group. You could have weak electrophiles like HBr, so I've got a delta negative, delta positive, so that end becomes my electrophile. I can get induced dipoles, so bromine, bromine, but I can induce a dipole on this by bringing it close to a double bond. So if I get it close to carbon, double bond carbon, I can induce a dipole on that. But these two are quite weak electrophiles. This is a much stronger electrophile, and it's one of these strong electrophiles that we need to react with our benzene ring. But benzene, rather than undergoing addition reactions, tends to undergo substitution reactions so that it can maintain the ring stabilisation. So this substitution would keep that delocalised ring structure. So the vast majority of the reactions of the benzene involve an electrophilic substitution reaction, and you need to know that. So the type of reaction is substitution, and the mechanism is electrophilic. So they undergo electrophilic substitution reactions. The nice thing about this is there's actually only one mechanism that you need to learn. We're going to use different electrophiles, but the actual mechanism is the same no matter what electrophile you're using. So in terms of the mechanism involving the ring, we're going to take the pi bonded system of electrons and we're going to use those to attack the positive electrophile. Now be very careful where you're starting your arrow from. Please make sure you're starting it from the ring of delocalized electrons, not from the sigma bonds on the hexagon. Now this leads us to an intermediate carbocation. And again, there are two very important things to notice here. We're breaking that delocalization, but we're only breaking it over the carbon where the electrophile has joined on. So we only break it over this one carbon. So this break should be facing the bond with the electrophile on it, and it should only cover that bond. We say no smiley faces in chemistry, so that is wrong. Do not do that. Also, make sure your positive is inside the horseshoe, not outside of it. So that's our intermediate carbocation. The next stage is to break the bond between the carbon and the hydrogen and use those electrons to reform the ring. So those pair of electrons go back into the ring. We get this structure, and obviously we've now got a hydrogen ion loose somewhere. Now this is our electrophilic substitution mechanism. The only thing which will change for the different reactions is it'll change how this electrophile is formed and how this H positive ion reacts at the end. So we're going to look at the first of these mechanisms on page 12, and this is what we call the nitration of benzene. So the first thing we need to do is we need to make the electrophile. So to make the electrophile in this case, we need concentrated nitric and concentrated sulfuric acid. We need to heat it and keep the temperature at 55 degrees Celsius. So sulfuric acid is such a strong acid that it's able to transfer a proton onto the nitric acid. So in other words, we get H2SO4, the sulfuric acid, reacting with nitric acid, HNO3, and we can get one of these hydrogens to be transferred on to this nitric acid. So we get HSO4 minus, and we've added a hydrogen, so we get H2NO3 plus. Now this nitronium ion is very, very unstable, and it very quickly loses a molecule of water. So we have H2NO3 positive, that very quickly loses a molecule of water, and we get the NO2 positive. That is my powerful electrophile. Now quite often you will see this written as a single reaction because this stage happens so quickly you don't really get any of this intermediate. So you'll find it more usually written just as sulfuric acid reacting with the nitric acid to form water and my HSO4 minus and my NO2 positive. Now in this case we say that the sulfuric acid is acting as a catalyst because it's not actually involved in the reaction, but it is involved in generating the electrophile. Then we get the same reaction that we've had before. We pick the electrons up from the ring and we put them on or near the positive charge. We then reform the ring, and do be careful you draw that horseshoe correctly so it's broken only over the carbon the way we've added the NO2 group, and we put the electrons back in to get our product nitrobenzene and to release the hydrogen ion. So that hydrogen ion is now free to react with the HSO4 minus to reform the sulfuric acid, and that's another reason it's classified as a catalyst, because it reforms at the end of the reaction, and our product is just nitrobenzene. Now you need to be careful, as I said, your reagents are concentrated nitric, this won't work with dilute, and concentrated sulfuric, H2SO4, and we need to heat it at about 55 degrees Celsius. Too low and you risk it not working, too high and you're likely to get multiple substitutions. So you're likely to add more than one nitro group onto the benzene ring if you get it above 55. So it's very important in these reactions that you control the temperature. So on the next page we're just going to draw out that mechanism for the nitration of benzene. So we're going to start with generating our electrophile. So I've got my sulfuric acid and my nitric acid reacting to form my water and my HSO4 minus and my electrophile NO2 positive. We need to generate the electrophile. It's never going to be able to be a reagent, and the reason for that is these are very, very unstable. Then we're going to take our benzene ring with its delocalized ring of electrons. We're going to take our NO2 positive group. We're joining onto the nitrogen, so we're going to show the arrow from the ring, remember, not the hexagonal carbon groups, to the NO2 group. We get our intermediate carbocation, where we break the delocalization only over the carbon I'm interested in. Our positive has to be inside the horseshoe. We get our NO2 joined on and our hydrogen. The electrons in the carbon-hydrogen bond go back into the ring to reform the ring, and we get our benzene ring with our NO2 group on it, and we have our hydrogen ion. That hydrogen ion then reacts with the HSO4- to form or reform H2SO4, and that is the complete mechanism. So that finishes this video just looking at the mechanism of the benzene reactions, that electrophilic substitution mechanism. It's a mechanism that comes up a lot in A-level chemistry exam papers, so you do need to practice it and get used to drawing it out, making sure you pay particular attention to where you're picking up the electrons from, where they're going, and making sure you're only breaking the delocalization over one carbon atom, that you've got the positive inside the hexagon, and that you've reformed your catalyst at the end of the process. In the next video, we're going to be looking at the practical of the nitration of methyl benzoate.